All right. Hello, everyone. Can I have your attention back? Okay. How's everybody? Good start for this week, hopefully. Okay, so let's continue with our discussion. We are on section 2.4, steady state response. And just to refresh your mind, we had a system, simple spring mass, single degree of freedom, only one variable. But this time we have an external excitation. This external excitation is a harmonic, either sine or cosine, doesn't matter. We draw the equation of motion and looks like something mx double dot plus kx is equal to f0 cosine omega t. And as I said, depends on the problem. This m may not be an m, it might be something, but a constant. Same for stiffness, which we call them equivalent mass, equivalent stiffness, and this f0 can be any number, all right? It can be even a moment, like the example that your TA solved you probably for you on Friday, and the rest of you who are going to attend today. This f0, it can be a moment. For example, a couple that is harmonically switching direction. So we solve this differential equation and we find out that the solution xt has two parts, the complementary solution and the particular solution, both function of time. The complementary solution, we find that it has a form, looks like a cosine omega nt plus b sine omega nt. We know what is omega n, and we know that a and b depends on initial condition. And then this xp, we solve it, and we find that it has a form, which is a constant, which we show it by x, and, or let me write down the whole things, just to be consistent. This part is x cosine omega t, right? This xp, and this x has a form which is f0 k minus m omega squared. So this is what we found. Make sure that whatever excitation you have, cosine omega t, this function has to be the same. And technically, we say the force and the motion of this mass, they are in phase with each other. Later, when we add other things to the system, these two might not be in phase. But right now, when you have an excitation, it means your mass is going to move ups and down with the force, all right? So if you have for this one cosine, let's say this is f0 cosine omega t, by mistake, you write here x sine omega t, it means that you are implying these two, the motion of the mass and the force, they are like 90 degrees out of phase, which is not the case. Here, always, whatever function we have, this is the same. And it's not our decision, it was what the math, when we solve the equation of motion, decide, right? But later you will see the cases where these two are not in phase, but not for now. Always these two are in phase, and again, that's because of the math. Now, when we look at these two equations, we know that this part comes from our initial disturbance of the system, right? So this is the, let me write it down, comes from the initial disturbance of the system. Disturbing of the system. Right? So initially we had a x0, v0, or we may not. It comes from there. But this part is permanent. This is, we say, this is permanent unless we stop the force, right? We stop the force. Otherwise, it's gonna continue forever. So the temporary part is gonna die away eventually because we disturb the system. Of course, we are dealing with an ideal system, but every system has some sort of friction or some sort of resistance in a spring, like friction between the, even, let's say, springs, coils, and air resistance and other things. We will say that this is eventually dies away. This part eventually dies away. So that's why people call this part a temporary or a transient or transient response. So transient response. But the other part, since it is permanent, it's going to be always there, and it is called steady state response. Right? So the transient or the transient, both people use both. I prefer transient. The transient response is temporary. It's not important for us. It's just maybe you run a machine. The machine is going to run maybe for days, but the transient response is for just the first few seconds. Sometimes it's important. Maybe it creates a shock to the system, which we will get to that part. However, in most of the case, the transient response is not really that important. And our focus mainly is for the steady state response. So this is what we are going to focus mainly and spend our time and energy thinking about. Let's see if we can plot this X and see if we can get something out of it. I'm going to write down X here is equal to F0, and I'm going to divide it by K. M over K omega squared, right? So I divided the numerator and denominator by K. And then I'm going to write it down. So if I look at M over K, right, I'm going to write it down here. We know omega n has a definition is square root of K over M. So I can simplify then this equation. X F0 over K is equal to 1 minus omega over omega n squared, right? Because we substitute this guy by, like M over K, we substitute 1 over omega n squared, because that's the inverse of that. This is 1 over omega n squared, right? So in this equation now, this part, F0, the constant force divided by K. It is, we can call it the static deflection, right? So as if I apply this F0 without any harmonic, then this amount, the spring is going to deflect. But this X, we call this X the dynamic deflection. In system, when we want to analyze them, we are interested in this ratio, right? Because we say, okay, if the system wasn't static, we probably have a reasonable amount of static deflection if I apply this force like a constant. So this ratio, which is an important factor for us, we call it M. So M is 1 over omega n squared. Okay, and since we care only about the magnitude of this number, because it can be positive or negative, we put it inside a bracket to say that we care only about the absolute value of this M. And it has a name, which we are going to call it from now on the magnification factor. Magnification factor. So it is a factor which depends on the system. As you can see, it depends on K and M because we have omega n in the system. And obviously, it depends on omega, how fast this system, this excitation is applying. I can plot these things. Let's plot it. It's easy to plot. You are familiar with this function, right? Maybe then we can remember it better. So we call this one M, and on x-axis, let's call it omega over omega n. Okay, it's just a simple function, 1 over 1 minus the variable. And you know how to plot it. So we need some key numbers here. If I look at these, so again, don't forget, this is the absolute value, right? So when omega over omega n is 0, like on x-axis, right? When I'm at the beginning, 0, this m is going to be 1. So maybe 1 is an important number. Let's show it here. And when omega over omega n is equal to 1, you can see this value m is going to be infinity. So then I need a little bit of a room here. So let's say around here. Which is omega over omega n is equal to 1. So the denominator becomes 0, so it is infinity. So this part of function is going to look like that. Then after I pass this number 1 from infinity, I'm going to come back. And then I can look at this one. When omega over omega n leads to infinity, this function is going to be going to 0. So then if I can do a good job, it's going to look like something like that. You guys agree? Go to infinity at 1 and then come back to 0. So it means if my excitation omega is so fast, yes, please. Remember we put like this absolute value there, right? Because we only care about the magnitude, but you're right. If you want to plot the actual function, it goes from the minus. But since of the bracket, the absolute value goes from there. So one thing that we can find out, if you apply a force, but your frequency is close to infinity, like the force is harmonic, ups, down, ups, down. If it is that fast, almost that we cannot see it, then the magnification factor is 0. It means it's not going to have any effect on the system, no matter how big the, let's say, the force is, which is not intuitive, but this is the case. Because again, the frequency of applying the force is so fast that we don't let the system to vibrate, right? Before, like, let's say I move it up, before I allow it to do something, I move it back down, right? If I move something up and down so fast. So another key value that I need to remember, so here is then, just let's draw that things. I noticed that my graph somewhere is intersecting 1. So we are interested, where is that speed of omega, right? When I'm saying speed is the speed of this force that I'm applying, omega. So if I set this m equal to 1, because it's absolute value plus minus things, you will find out omega over omega n is a square root of 2. So it means this number, which is a critical value, is a square root of 2. Now you tell me why this number is critical, like this is square root of 2. Any idea? Like whenever we want to do a design, this square root of 2 is a key number that people look at it. They look at their system, so they decide this omega over omega n, if it is bigger than a square root of 2 or smaller. Why is that the case? Sorry, go ahead.
Yeah, if it's greater than root 2, then the magnitude is 1. So you're kind of
all right, good point.
Or if it's greater than 2, then
Exactly. Yeah, that's correct. Exactly. And someone here want to say? Not overdamped. Overdamped is a different terminology, but you are on the same path. That's correct, both of you. When we are bigger than a square root of 2, it means this m is less than 1. And this is something that we like. We want always this magnification factor to be less than 1. We want less vibration in our system. All right? Unless it is that system that I showed you at the very first day, that vibrator that I had, right? Unless we want the vibration, that's a different story. Always we want to remove vibration or reduce it. So we like to have, when we design something, to have m less and less. So for design, then I will write down this omega n over omega n. This should be bigger than a square root of 2. For design purpose, we try to set omega over omega n bigger than the square root of 2. Maybe we don't have control over omega. Maybe that's the speed of, let's say, a washing machine, or the speed of a motor rotating. So we don't have any control over omega, but we have control over n, over omega n. Sometimes maybe we can add extra mass, reduce mass, or sometimes we can change the stiffness. So by a slight difference in omega n, the whole story changed. And in fact, it is true. In industry, people, they look at the system, they measure omega n, because in industry for big machine, usually we measure omega n. And that's your last topic in this course, how to measure omega n. We measure omega n, we look at the system, we measure omega n, and then we decide, okay, I'm at the critical point, maybe even I'm at 1, that's bad. Then simply adding a mass to the system, even depends on the system, a slight mass, or maybe adding a stiffness or reducing a stiffness can shift us from this 1. And even better, if you can be after a square root of 2, then it means less and less vibration. Okay, any question for this part? Are we good? Because this is important, and what you need to remember from this part is this magnification factor formula and this graph, obviously. Always have this graph in your mind. How does it look, and the critical point on this graph. All right. Another things that we come across in vibration a lot is the base vibration. And that is when something is exciting the base of the system. It might be, let's say, in a factory, the floor shop, because of the adjacent machineries, there is vibration on the floor. Or it might be just your car driving on a road and the vibration comes from the road. So that's a very common thing, and we call it base motion or base excitation. And since we are in the very first topic, still we are in harmonic base motion. Of course, you may say road is never a harmonic, right? It's not sinusoidal, but later you will see, if we know how to solve this one, we will figure how to solve a road vibration. So how can we deal with this problem? Like always, 3 steps, the kinematics. So this system is obviously a 1 degree of freedom. If we are lazy and we don't show it, it doesn't mean that it's not there. In fact, this system, if we want to be more, let's say, accurate, we should have said that this system, because the schematic only shows X, it means that I sort of prevent any motion, lateral motion. Right, so I put it maybe inside a rail or something. But for simplicity, we just don't show it. As long as we just show X, it means just one motion. And on a base, I have a motion which is Y, and this Y obviously is not constant because otherwise the problem will be just a simple static problem. So let's assume that this is a constant. Let me show it by capital Y and cosine omega t, because we said it's harmonic, it goes ups and down. Right? So this omega then is a constant. Any number, right? 10 cosine omega t, and omega is another value. So that's the kinematics, the first step. This is how the system is going to work. Second, we draw the free body diagram. So let's quickly do that. So the free body diagram for me, I have the mass here. So I look at the spring. When this system was in a static mode, because of the weight, there are some pre-compression in a spring. So I don't show the weight, and I don't care about these static deflection, because I know eventually they are going to cancel out each other. Something that I want your attention, take a look at this spring. So this spring, you can see it has been extended by X, and it has been compressed by Y, right? So then the total deflection is the difference between these two. Therefore, my spring force is K X minus Y. So that's my free body diagram. And remember, at equilibrium, as the problem shows, this is our reference, and this is the positive direction for X that we decided. That's the free body diagram. So when you draw the free body diagram, make sure to show your datum and the coordinate. And there is nothing wrong if you show it up, like upside down. Then the direction of the force has changed, but eventually everything is going to be the same. So sum of the forces must be equal to m x double dot. So what do I have? Minus k x minus y is equal to m x double dot. And I simplify this one. So I would get mx double dot plus kx is equal to ky, and I replace y by y cosine omega t. If you're writing notes, try to save the space, so do not pass over that transmitted force. We need that space for other calculations. But doesn't matter, if you need extra space, always you can go to the last pages. So this is the equation of motion, or the differential equation of motion to be exact. But we are lucky because it exactly looks like something that we know. This is the mass, this is the stiffness, but this time our F0 just has this form. K, a number multiplied by another number, right? So this is our F0, which means we can still use the previous equation that we developed. So let me write it down. So xt will be then x cosine omega t. That's the response of the system. And we know this x is, so this is our F0, right? So we learned that x is F0 k minus m omega squared. Previously, when we solved this problem, I just need to replace F0 by k y, and this is k m omega squared. So if I simplify it a little bit, I can write down x over y is 1 over 1 minus omega n squared. All right, x, y, we divide by k, yes. Okay, so another again key formula, if I have a base motion, the ratio of the dynamic deflection to the base motion, right? This is the base excitation. It is the base amplitude, whatever number it is. And this is the dynamic vibration or the dynamic motion amplitude. So the ratio is 1 over 1 minus omega over omega n squared, which we know what it is. It is the magnification factor. So the same magnification factor as before, right? So I can plot then these things. Let's do it over here. So we call again M 1 minus omega n squared. You know how it looks like. So I don't need to spend time on this one. And this is M or X over Y. And this is omega over omega n. And the same story, if it is bigger than the square root of 2, then we are happier because it means less vibration is going to transmit to the base. Sorry, to the to the system M. Let's say M is your car and you want less vibration. I'll let you take notes. Okay, so now we want to do something else with these things. We are interested to see how much force is being transmitted to the base, because it's maybe some things that we are also interested. Why? Because let's say this is a car and I'm interested to know how much force from the vibration is transmitted anyway to the chassis of the system, because I'm going to later, let's say, design some brackets or other things. So I'm interested in the forces that being transmitted either to the base or the same force, the reaction force to the main mass. So we are going to talk about the transmitted force to the base. So this force, let's call it Ft, so we don't getting confused by the excitation, like F transmitted to the base. And we know this force from our diagram is going to be Kx minus 1, right? So that's the force. And we know it is a function of time, because these x and y, they are a function of time. You guys agree? So let's move back again. The forces, like in this spring, is K stiffness multiplied by deflection, and deflection, you know, is x minus y. So this x minus Kx minus y, I just showed here in this equation for you that it is equal to mx double dot. Right here. Kx minus y is mx double dot. Let me substitute that one there. and I have a minus mx double dot. Okay, so far good. So this is a force that I have. I call it Ft in order not to get confused, and I know it's a function of time. Luckily, we find this xt. We know this xt is x cosine omega t, right? And x has a formula, which we know what it is. So if I take the derivative x dot, it's going to be minus x omega sine omega t, and another derivative x omega squared cosine omega t. So let me substitute that things there. I get rid of the minus sign, mx omega squared cosine omega t. And x, yes, that's correct. And I don't have the minus sign. So this is the force between these two, between the mass and the base, or the force that's being transmitted to the base. Like always, we care about the magnitude of this force. So then I would say Ft, the magnitude is mx omega squared. I substitute x by the formula that we found, m omega squared, which was f0. Oh no, sorry, x. This wasn't f0, right? X, what was x? It is here. This is what we found for x is y over, or let me write the original one. Ky k minus m omega squared. Ky k minus m omega squared. Okay, I hope I didn't make a mistake, but please check my math to make sure. I just substitute this x by what we found for x. Now let's do some manipulation here. If I write down these things, ft over ky, then I would end up with omega m omega squared k m omega squared. Why do I have an extra m here? Okay, I have an extra m here that I'd like to get rid of. So let's move back here. So far good here, we have ky, k minus m omega squared, so far good. So I found x, and then it is y. Okay, so let's continue. This is correct. Now let's divide everything by k, and let's see what will happen. M over k, omega squared, and this is 1, m over k, omega squared. Oh yeah, that's correct. It's even better. So from here, if I simplify it one more step, I will get omega over omega n squared, 1 minus omega over omega n squared. Okay, remember this m over k, right? This m over k, we know that omega n is the square root of k over n. Okay, so what we found here is that the transmitted force divided by ky is equal to omega over omega n squared 1 minus omega over omega n squared. That's again another key formula in vibration. Why it is key? Because this ky, it is called a static force. That's a force if we apply just a deflection in a spring, right? That's going to be K stiffness multiplied by 1. And this Ft is the transmitted force. Or to be exact, the dynamic transmitted force, the force that it comes from vibration. So the ratio of these two are important for us. We like to know if we have a system, what is this ratio? And since again, we care only about the magnitude, we just put it inside this absolute and we care only about the absolute value of that. All right, now let's plot these things because always we like graph or plotting things because then we can interpret it better. So I like to plot these. The whole things is also called the magnification factor, but that's a different magnification factor, right? So the whole things, we call it the MT. Magnification factor for transmitting force. Right? So MT, so we don't get confused by the other M. And the x-axis is omega over omega n. Now try to plot that thing. So obviously I know that I have these one things here, which everything goes to infinity because the denominator becomes 0. And probably I have these one things maybe there. And then when omega over omega n is 0, this time is not 1, it's 0, right? When omega over omega n is 0, is 0. At 1, it goes to infinity. So it's going to look like that. And then at infinity, you can look at the equation. You have a variable up, one down. It's going to then lead to 1. Okay, so this MT, again, remember, this is the ratio of the force to the static force. So this graph shows the force, the previous one shows the vibration, and these two are different. You can see from the result. Their formula also is different. So I may throw a lot of formula for you, but don't worry, we are going to repeat these a lot. It's just matter to follow what's happening, and if you understand what's going on, then that's good enough. And as you can see, the math is not really that complicated. Yes, please.
How did you reduce from MX and MX squared to MX?
Like here at the beginning? Okay, so this is mx omega squared, right? So this x, because we know that this x double dot is this guy, right? So far, you're good up to this point? So this x, we calculated. If I go one slide back, this is this x that we calculated. So this x is equal to ky, k minus m omega squared. Why? Because we said that this equation is exactly similar to what we had before, except this time the F0 has a different shape. It is K multiplied by Y, right? So then in fact, what I did, I substitute this X by this value that you can see here, K, Y, K minus M omega squared. So we get to that point. And then the rest is just math, right? We manipulate these things because we wanted something nice and clean, something that we can plot. All right, so let's quickly solve one example together. Yes, please.
Yes, sorry. So did you, for the x of t, did you only include the particular solution because there's no additional?
Right. That's a very good question. Thank you. Remember when we said at the beginning that we are going to focus only on a steady state response? I said that the transient response is not really something that we care too much because it's only the first few seconds when we vibrate, when we excite the system. Let's say you turn on your motor, that's just going to be first few seconds. That's why we call it transient. Not that we don't care about it. There are times that we care about it, especially in courses like control. But here in vibration, no. And that's why we are going to shift our focus for most of the problem that you will see on XP or the particular solution. All right, so let's solve one example together. I give you a minute to think about this and think about these three steps. How these things is going to move, the kinematics, understanding the mechanism, that's the first and important step. Then free body diagrams, and then the rest is just come straight. Remember always the concept that I teach, they are only mass and a spring, but the actual problems, they are not mass and a spring. There is a mechanism involved. But if you simplify it, you are going to end up with the same equation. It is just that the shape of this M and K stiffness and F0 is going to be different. But if you follow the step, you are going to end up with Mx double dot Kx is equal to F0 cosine omega t. Of course, here our variable is theta double dot. It means it's a rotating system. So instead of x double dot, it's going to be that. But always we are going to end up with that. So if it is something different than this, it means we've done something wrong. Okay, let's quickly do it together. And then whatever time we have, you could finish it on your own later. So if I look at this system, there is this XB. So it goes under category of base motion. But as I said, we don't care what is what. We just draw the free body diagrams, but you can think of it as there is a base and you are moving the base. So the difference between base motion and force excitation, remember, in base motion, let's move back. In base motion, you have a displacement here, right? This YT is a displacement, but here you have a force. So that's the only difference. A force, a displacement when we talk about base motion. Like in this example that you're solving, here you're not applying a force. You are applying a base motion. Maybe you, let's say you hold this point B and move it left and right, right? Maybe this B is 10 millimeters. See what I mean? It's not a force. It's eventually it's gonna transform to a force because you have a spring between, but you are applying a base motion. But for us, we just let the math to find out everything. We just draw the free body diagram. Let's do that. As I said, we decide for a variable. Our variable, the question decided for us. So it's theta, and it's moving to the right as a positive. Right? For your own, let's say later when you solve it, you can decide this theta to go to the left. Doesn't matter, but the free body diagram, of course, change. So if it moves like that one, then I know this pendulum is going to swing like that. And probably this mass is going to, let's say, move a little bit and come to some place, let's say there. Let's call this displacement, let's call it x. So it moves there by how much x? Since we are still in single degree of freedom, this is an alarm for us. Why do I have two variables here, x and theta? So there should be a relation between these two. Otherwise, it is 2 degrees of freedom, and we have no idea how to deal with a 2 degrees of freedom. So far, we learn only to end up with only one equation, and that equation should have only one variable. Looking at the kinematic of this system, it's not difficult to figure it out. Like this mass M2 is attached to point D, and this is attached to point C. Right? And because again, we are in vibration, everything is in a small motion. Easily, I can write down that this x is 2L over 3 theta. You can, or you can be, let's say, very meticulous and then write down here theta and say that, okay, here I have a triangle. In this triangle, I can write down that sine theta is equal to this distance, which is equivalent to x, right? Because how much the C is moving, D is moving, and that's x. Sine theta is equal x over 2L over 3. Remember, because again, we are in vibration, we assume everything is small, although this C is going to move up C prime. And we know in vibration, this sine theta is equivalent to theta for us. Or that's okay if you just write down 2L over 3 theta. So that's the first thing that we have taken care of. So we have only one variable, theta, to be worried. Second part is the free body diagrams. Let's quickly do that. Or maybe because the next teacher is coming, I'll let you guys to do the free body diagram on your own. And then we can compare your solution. Please draw the free body diagram, draw the equation of motion, and try to see if you ended up with the same form equation. Have a good day, and if you have any question, I'm outside that door because we have to leave quickly for the next class. Yeah. All right, good question. For your midterm is going to be section 1 and section 2. Everything's up to section 3. Right? Or everything that we cover this Wednesday, until the end of this Wednesday.
Will there be a practice midterm posted?
Say it again.
Will there be a practice midterm posted?
I'll try, but it's going to be the same question that I posted. Same range question.